Now, let's introduce very briefly the Galerkin approach to finite method. It should be noted that Galerkin approach is more general and thus important. However, the variation approach to finite method is better of the two to study the basic approach without any mathematical ambiguity, especially for the beginners, who I believe are acquainted with extremization of functions. That's why we studied the Ritz method first. Anyway, now you have not left much to study Galerkin approach to FEM if you understand every inch Ritz method. From now, we are going to generalize our variational approach to finite method. The solution domain is discretized into n-1 elements by n nodes. The nodes are classified into two groups, one for nodes on essential boundaries denoted by eta bar, and the other for nodes with unknown nodal values denoted by eta prime. Approximating the unknown function by interpolation functions with their corresponding nodal values and substituting this approximation into this functional, we reformulate the original extremization problem in infinite dimensional function space as a nonlinear programming problem in finite dimensional vector space like this. Yes, of course, this can be easily handled by human being. Applying this necessary condition to the objective function in the approximated nonlinear programming problem before imposing essential boundary conditions, we can get this intermediate finite element equation. After imposing essential boundary conditions, we obtain these finite element equations. Of course, this expression is based on global description of FEM, which is better in terms of understanding a bigger picture of FEM, because this description is next to approximation methods, which form the theoretical backgrounds of finite method. I'm sure that you can imagine the local description of the same formulation based on mapping everything from global to natural coordinate systems in a similar way you were taught previously. Galerkin approach to FEM starts from this weak form. We approximate the known function as a linear combination of interpolation functions nj with their corresponding nodal values pi j. We also approximate the weighting function as a linear combination of the same interpolation functions ni with their associated arbitrarily constant wi. Plugging these two approximated functions into this weak form, we can get these final equations before imposing essential bound conditions, which are the same with those of this method. The detailed process and procedure to construct final equations and obtain the solutions in Galerkin method are absolutely the same with those of the Ritz method. Therefore, the details about them are skipped. Finally, I will summarize some characteristics of finite element predictions. Linear differentiation is simplified to a set of linear equations. The number of these linear equations should be the same as that of knowns. For example, linear elastic deformation problem in solid mechanics is formulated by linear finite element equations. Likewise, nonlinear differentiation yields a set of nonlinear equations. For example, flow analysis problem in fluid mechanics and metal forming engineering is formulated by nonlinear finite element equations. The primary state variables, which are direct solutions of the finite element equations, include temperature or rate of temperature, displacement or velocity, hydrostatic pressure depending on the problem formulation, and so on. The secondary state variables include heat flux, strain, stress, reaction force, and the like. The accuracy of the primary state variables is relatively high compared with most secondary state variables, which are calculated from derivatives of the primary state variables. In case of linear elements, which are prevalent in engineering analysis, discontinuity of derivatives of the related functions occurs along the element edges, and thus elemental values are usually saved at the center of the elements on behalf of the elements. Nodal values of the secondary state variables should be approximated by so-called smoothing process in a numeric way, for example by least square approximation. It should be emphasized that more or less error is inevitable in this kind of smoothing process. Therefore, some numerical oscillation of stress or strain is inevitable, which can be more serious if bad quality of finite mass system is employed.